Hi, everyone. So I want to first thank, all of you guys for joining today. Just to let you know, we are going to wait another minute or two for any last minute people to trickle in. And I am going to mute everyone for the duration on the presentation part of this here. And then at the end, we'll open up for any questions you guys might have. So if there's a particular slide you want to reference, just write it down and we can go back to it. So otherwise, you won't be able to talk to me during the presentation. All right, I don't really see anybody else trickling in, so we'll go ahead and get started. Today's presentation, we're going to dig really deep into pile groups and how we look at those and how they're maybe beneficial. So let's kick this thing off. Maybe if it'll change slides, there it goes. First, we're going to have just a quick introduction to the different types of foundations that we commonly use. Go into all the different loaded considerations that you need to look at when you're designing for a foundation. And then we're going to dig into, okay, what are the group effects when you've got a pile group? And more particularly, what's the lateral response when you have this pile group? And we're going to wrap it up by looking at designing of the individual piles sort of in that pile group once you've got all your group effects figured out. And then we'll open it up for any questions you guys might have. So different foundation types. Shallow foundation is probably going to be the most typical foundation you'll see. It's mostly found in like residential applications on homes, but it's definitely not uncommon to have them in light commercial and even moderately loaded commercial structures as well. So something to consider with a shallow foundation is, it doesn't necessarily refer to its depth, but really it's referring to the ratio of the width of your foundation to the depth of the foundation. Where if the width of the foundation is larger than the depth of your foundation, that's when you would consider it to be a shallow foundation. So some common synonyms that you'll see for shallow foundations is spread footing, continuous footing, perimeter footing. There may be some more I'm missing there as well. But typically these types of foundations, they will run along the perimeter of the footing and be a continuous pour for basically the entire structure. So the pros of a shallow foundation, the first obvious pro is it's very cost effective and cheap to install these. There's not very much excavation, and there's a very vast history of how these perform and the design standards that go along with doing this type of foundation. So some of the drawbacks of a typical shallow foundation is you're relying on the surface soils, having the strength and settlement characteristics that you need for your project. So if your loads are too high or the soils are too compressible, this may not be an appropriate foundation type if you have those situations. And the other drawback for a shallow foundation is that upper sort of 10 feet of soil is highly susceptible to volume changes, whether that be from frost or just water infiltration with the changing of seasons. So as this soil shrinks and expands, it is going to impact that foundation if the soils, at that foundation level are putting, additional stress on it or shrinking down and causing settlement. So those are issues that you may run into with just a typical shallow foundation. And now we're looking at, another shallow foundation type that would be more for like a light commercial style building. And this is like really any structure that's column based. So like pole barns, warehouses, structures like that where you've got basically a series of columns that are providing the support for the structure. So when you have these footers, they're basically isolated at the columns, at each column location, and they're not typically tied together, but they can be, and we'll talk about that in a minute. But you'll see these referred to as many different things: individual footings, isolated footings, column footings. They're all referring to just these isolated concrete footings located at each column. So the pros of these, similar to the traditional shallow spread footings, these are very cost effective. You're not going to have to do a lot of excavation, and there's lots of, documented design aids to help you design for these isolated column footers. Now the problems when you have a structure like this and you've got all these column footers that are separate and they're isolated, you're basically opening the door for, maybe the corner pile or the corner foundations to have more settlement than the middle foundations because there's more load concentrated on the corners of the structure. And the other thing is, as these structures get larger and larger, your loads, they have to increase as a result of that. And with an increased load, you're putting an increased bearing stress under the soil. And this may result in just having to have a very, very large footing size to the point where it's not really feasible to use this without considering, some deep foundations or other foundation elements that you have to add. So this is, like I talked about, you can tie these individual column footers together with grade beams. It's actually a great way to sort of tie together the stability of the entire structure. You're providing a more safe, efficient load path for the structure. And really what you're doing here is you're helping to mitigate this differential settlement effect by tying these footers together. If this one comes down, it is tied to this column as well. So they're going to end up sort of settling more uniformly, which is definitely, advantageous for most structures to have a more uniform settlement than a differential settlement. And you can also run, basically as many grade beams as the structure requires, depending on soil type and everything. And, another benefit you'll have from running these grade beams is they're going to provide support for your slab so that your slab doesn't end up with differential settlement or cracking, kind of throughout the entire floor of the inside of the structure. So another type is shallow mount foundations. So now instead of individual column footers or even tying those footers together with grade beams, in this situation, you've basically got a 1 foot thick plus, as like a minimum slab for the, across the entire footprint of the structure, tying all the columns and all the foundations together. And these are really, really useful for helping distribute the load across the entire, subgrade beneath, which also helps to, mitigate that differential sediment I keep bringing up because that can be very damaging to the superstructures. And this is very common in commercial structures, especially heavily loaded ones, and structures with basements as well. So you'll see these referred to as structural slabs, rack foundations, mat foundations, pad foundations, and they're basically all referring to a one big giant foundation that covers the entire footprint of the structure. So the pros of this type of foundation is you're reducing the stress in the soil by having a large area to bear that load. Because stress is force over an area, and if we increase that area to the entire footprint of the building, you're going to actually decrease the stress, across the entire soil beneath it. And it's very useful when the mat is leaning more towards rigid to help mitigate that differential settlement. So some of the cons with a foundation like this is you're going to be susceptible to uplift forces, to water pressure or seismic activity. And you're also, could be prone to some material loss at the edges of your foundation from water seepage. And then with the more flexible this mat foundation gets, the more likely you might see some differential settlement. So whenever you've got a foundation this large, it's going to require a lot of reinforcement to basically have it be a rigid foundation. And if you don't achieve closer to that rigid condition, that's when you open the door to this thing still having differential settlement issues, even though it's on paper a good way to mitigate it. If you're not designing it as a rigid mat, then you can still run into those differential settlement issues. So now we'll look at deep foundations. So whenever you have a project and you've basically gotten to the point where the loads from the structure are too high to be resisted by the soil, or you just have highly compressible soils where excess settlement, differential settlement. When you have these types of concerns, that's whenever you switch to a deep foundation option. And there's many different types of deep foundations. So driven piles, probably everyone's familiar with. These are going to be very common in large, heavy structures, bridges, big buildings with very high loads. They can be made of steel, timber, or precast concrete. And usually it's just a crane with a big diesel hammer that just pounds it into the ground. And the amount of force it's taking to drive that pile is correlated to how much that pile is going to be able to hold. And then another type is caissons, auger casts, drilled shaft, and all these they might have different installation techniques, but the outcome is a large diameter bored hole that gets filled with concrete and reinforcement. And basically this acts as an underground concrete column to help support the structure. And then, the other two types for more lightly than moderately loaded structures are helical piles and micropiles. And again, you really use these types of deep foundations where the surface soils are inadequate for, whether it be load bearing or settlement. That's when you pivot to using some type of deep foundation solution. So all deep foundations, regardless of which deep foundation you have, they're all going to get their capacity through either one or both of these methods here. So skin friction, that's going to be the interface of your pile interacting with the soil around it. So in this example to the right, this is actually a helical pull-down pile. So you have your helical plates down here, but after your lead section, there's actually a grout column that gets pulled down. And that grout is going to bond to those surrounding soils and provide resistance through skin friction. And the other type of resistance that you're going to get is through end bearing. And in the case of a helical, the load gets transmitted through the shaft and then onto these plates, which then bears down into the soil beneath it. And you can see in this case, this is a 3-flight helical. So there's basically 3 sort of end-bearing zones. If this were a driven pile, you would still have the skin friction through the interface of the steel interacting with the soil around it. There's still going to be friction there. It would be less than a grout bond, but you would still have that friction. And then again, for a driven pile, you'd only have one bearing zone, and it would just be like the tip area at the bottom of your pile. But I chose this example because this sort of it's a good visualization for how you can really have both with a pile, where you can have your skin friction bond as well as end bearing at the bottom. So pros of deep foundations, they can be installed to provide high capacity in almost any situation. Eventually, you're going to run into some material that is either stronger soil or rock, and when you hit those materials, you'll eventually be able to get your load capacity. Now, there may be soft soils and buckling concerns or liquefaction concerns that you've got to design that deep foundation for, but you can almost always design around that one way or another. to basically achieve the capacity you need using deep foundations. And then another pro is you can really get a lot of tension and lateral support from a deep foundation element. Now, if you've got a shallow foundation, you basically only have the tension support from the weight of the building. So if buoyant forces or anything else, wind loads, if those types of things cause enough uplift and it basically overcomes the weight of the structure, that could be very damaging to the structure. And deep foundations are probably the best way to control differential settlement because you're taking these surface soils, which might tend to vary a lot more from one location to the next, and transmitting it to the more uniform sort of deep subgrade down here, where settlement's going to be more predictable and uniform sort of across the entire structure. So the cons of using any type of deep foundation element is it's just going to be more expensive than a shallow foundation. But if you're in a situation where you need deep foundations, you're really not going to have much of a choice. There are some ground improvement methods you can explore as well. But really, when you're in this sort of situation, the cost is it's understandable because that's really the only option in these cases. So the other thing is, depending on what type of deep foundation you're using, you may have installation challenges, or whether that be to difficult soil conditions or just like headroom conditions at the site. And then you're also going to have large equipment for some of these different pile types. So helicals and micropiles, those actually use relatively small equipment, which helps mitigate some of those challenges. But if there's difficult soil conditions, it still could be problematic either way. So let's keep going here. So now we're going to talk about sort of the different loading considerations you need to look at. You're always going to have dead loads. So dead loads are permanent loads as a result of the materials used in the structure. So, if you build a building, you're always going to have the walls and the roof structure and all that. None of that's going to ever go away. So those are called dead loads. Those are permanently acting on the foundations. Then you've got live loads, which are transient. Sometimes they're there, sometimes they're not. And these are a result of occupancy, so movable objects, furniture, people, anything that may or may not be there on any given day. And then I want to take a quick second to talk about LRFD and ASD, and I won't stress on this too much. Foundation design is almost going to always favor using an ASD approach rather than an LRFD approach. And from here on, we're going to be discussing this from an ASD mindset, where we're talking about allowable loads, ultimate loads, and a blanket factor of safety. And the reason we do this for geotechnical design is when we look at the load factor and resistance design, this is actually sort of more precise than the ASD approach. But the reason for that is this is useful in steel design because we know with a high degree of certainty what the resistance of the material is. So if you're looking at a steel beam, you're pretty certain that it's going to have the strength that you need. But when you're talking about soils, and this resistance factor, or this resistance factor here is basically taking into account those uncertainties, right? So when we have a soil resistance right here, the uncertainty in that is much greater than the uncertainty you'd have for like a steel or even concrete and wood design as well. So that's why we like to stay in the sort of ASD design space for when you're looking at foundation loads. So the main sources of the other loads that you may see in your structure outside of your dead and live loads are the roof live loads. So whether that be from rain or anything else that may be on the roof, and then snow load. You can see if you've got some snow on the roof of the structure, that is going to put some load down to foundation level. And then wind loads will be acting on, usually one side of the building at a time, but they can basically affect the entire structure when those wind loads hit it. And then earthquake loads through ground movements sort of beneath your superstructure and below grade. And when these soils are being oscillated back and forth, it's going to have a huge impact on the demands of your foundations. So some of these loads, in particular the wind loads and snow loads and earthquake loads, they're going to be highly dependent on where the project is located geographically. So obviously, if you're in upstate Minnesota, you're going to have a higher snow load than you would in let's say Florida, where you effectively have zero, like we're seeing here, versus up here it gets all the way up to 70. And these numbers are in PSF. So up here we're saying at like the peak snow season you could have up to 70 PSF of load on your roof structure. And down in Florida, where you basically don't get any snow ever, you're obviously going to have zero. And this comes even more into play when you talk about earthquake loads. And this is really a dense topic, so I'm going to be brief here. But where you're at in location to any faults that are nearby and the type of faults those are, as well as the soil conditions and rock conditions at the project site, this is all going to impact sort of how the ground movements get transferred up to the surface, at that specific site. And really, this needs to be determined by a qualified geotechnical engineer, with sort of the main important factor that we're trying to uncover is the peak ground acceleration, because a force is mass times acceleration. So we need to understand what sort of acceleration these ground forces are exerting to be able to back figure, okay, what's that mean for the load on my foundation? So when you're determining your foundation loads, you're always going to want to do some type of load combination, whichever governing document is relevant for your project. I'm showing the IBC load combinations to the right, but you may need to use ASCE or a local building code. So it's important to understand what's sort of going to govern for your project. But really what you're trying to identify is the worst possible design case. So, I mean, you may have earthquake loads and wind loads, but that doesn't necessarily mean you're going to have a hurricane gust of wind during an earthquake with a foot of snow on the roof at the same time. So some of these get factored down or omitted when you're looking at these different load cases. And the reason for that is, you don't want to be so totally over conservative that it drives the cost up. So these load combinations are usually fairly similar from governing body to governing body. And it's really just the combination of all those load types we just talked about. So once you've determined sort of what your governing design case is, you really want to model the entire structure. And the desired outcome of modeling your structure like this is you want to understand what the column reactions are at the base. Because how these columns are imparting the load on the base is going to be, essentially the load that the piles are going to see as well. So understanding, how all these loads end up right here at the foundation level is going to be the most critical. And whenever you're doing simple structures, you can do this by hand pretty easily. But as your structures get more complex or your load cases get more complex, it's probably better to use some type of computer modeling approach to determine what these loads are going to be. And this is sort of the outcome that we're after. We want to know at the foundation level, how much compression is this column going to be putting on the foundation? And then is there any tension as a result of wind loads or blowing forces or whatever it may be? That could obviously impact the structure as well. And then shear loads are going to be very important to understand. And these are the lateral loads. So how much is this base trying to slide over? These are typically a result of your wind loads as well as seismic loads. And then you can also have bending moments that are acting at the base of these as well. And these are typically a result of wind loads. Earthquake loads typically only have a shear load that will be imparted in the foundation, but wind loads, you'll definitely have a moment, and we'll talk about that a little bit more. So now we're going to dig into sort of the group effects and lateral response when you've got a pile group. So when we talk about pile groups, it's important to to first make one pretty critical assumption. It's that your foundation is a rigid foundation. And the reason we say this is because rigid foundations and flexible foundations are going to respond way differently to loading condition. And the IBC is actually suggesting that anytime you're using a pile group, you should design it so that you've got a rigid pile cap. And it's not to say that you can't use a flexible foundation, but sort of a more rigorous analysis approach is going to be necessary if you do have a flexible foundation. You'll need to use, finite element modeling to see how that's going to end up, imparting load into your piles, and it's much more involved than going with a rigid pile cap. So what I have shown here is the Hettingi method for determining the rigidity of the foundation, and basically the critical things here are the foundation size, so the width of your foundation, the modulus of subgrade reaction, so how that soil is going to respond whenever you load it, and then the modulus of elasticity, so the stiffness of your foundation itself. So foundation size and basically the stiffness of your soil and how those interact together is going to paint the picture on, is this going to act as a rigid cap or is this going to act as a flexible cap? And you can obviously tweak these if necessary for your specific project to basically ensure that you've got a rigid footing, but you really want to be, at least in the intermediate, if not preferred, to get all the way to the rigid condition. So the International Building Code actually has a whole section on sort of the stability of structures, and deep foundations should be braced to provide lateral stability in all directions. So, what does that mean in terms of how do we need to design our pile caps? Well, basically, you need to have at least 3 elements per pile cap if you've got an isolated pile cap, and these elements cannot be more than 60 degrees apart. So, essentially, an equilateral triangle layout centered over your column is always going to be the most stable approach. Obviously if you've got more piles, it'll be even more stable, but this is sort of the minimum acceptable criteria for a foundation to be considered stable and braced. Now you can achieve stability with only 2 deep foundations in your pile cap, but that would involve sort of grade beams tying the structure together in the opposite direction. Because if you have a pile, like if this pile was gone, you would only have stability in this sort of direction, that's left-right direction, and the up and down direction. You wouldn't really have much stability because the foundation would be allowed to sort of rotate around your piles if you don't have anything to stop that rotation from happening. So whether it be the addition of having that 3rd pile or even a 4th pile, or tying it together with grade beams, you've got to have stability in both directions for your structure to, respond the way you'd like it to. So now we're going to look at, how do vertical and lateral loads get distributed into your piles. So going back again to that rigid cap assumption, if your pile cap is rigid and it deflects downward, it's going to have to impart an equal stress on both of these foundations here, both of these deep foundations. So in this case, if we have a 100 kip load imparting on this pile cap with 4 piles on it, each pile would theoretically have 25 kips on it. Now, if this were a flexible foundation, and especially if this were a flexible foundation and this load was offset, that would not be a true statement anymore. So for simplicity of design, when you have these rigid caps, it makes it very simple to say, okay, I've got a 100 kip load. Each pile is going to have 25 kips. And the same is true for a lateral load. And I've actually got the arrow sort of pushing on it right here. But it could also be applied sort of at the column up here. This would be more of an earthquake load situation. And a lateral load being applied up here would be more of a wind load situation. But regardless where you apply the lateral load, if you've got a rigid cap, it is a safe assumption to assume that you're going to be equally imparting load in all 4 piles sort of the same reasons that's true for the vertical, is that this is going to move uniformly and rigidly. So any stress that this file sees from the movement, this one is also going to have to see that same sort of equal stress. So taking another deeper look into how this moment gets transferred into your piles. So what I've shown here is a fixed and cantilevered beam. And for the sake of this discussion, we'll consider this to be a pile group down here, and this to be a wind load, acting on the side of the building. So obviously this is, horizontal and columns are vertical, but this sort of is a nice visual to see what we're going to talk about here. So when you apply a load to the side of the structure, it's going to uniformly, like a wind load, it's going to, for the most part, uniformly distribute that across the entire end. But what does that mean sort of at the base level? And that's why I wanted to do this because, or, show it this way, because these cantilever beams, this is a very common shear and bending moment diagram that you guys might be familiar with. You know that if you've got a load acting down on your cantilever, you're going to have a shear reaction at the base as a result of that load. So the same is true for if we have a wind load hitting the side of the building, you will have a shear load that's acting at the base. But it's not just a shear load. You've also got a bending moment that this connection needs to resist. So this is going to want to bend downward, and essentially, let's go to the next slide now. When this load acts on it, and again, consider this a pile group down here. Whenever this load is acting on it, it's essentially trying to pull up this top row of piles, we'll call them, and push in this bottom of piles. So, again, if you flip this 90 degrees and this was a pile cap, that would mean some of your piles are getting pulled up in tension and some of your piles are being pushed down in compression, sort of as a result of this lateral load and bending moment at your base. You actually end up with tension and compression loads because a rigid cap cannot transfer a moment as a bending moment to the piles. The rigid cap is going to sort of absorb that moment and transfer it into compression and tension load in those piles. So we can actually figure, what that increase in load would be from that bending moment you've got at your base. So, you've done your analysis and you know what your maximum moment is. You've looked at all your loading conditions and you've got now an understanding of what the moment loads are in the X and the Y directions on your structure. Well, now if you know how many piles you're planning to use in your pile group and their layout, this may be an iterative process to sort of get to a design that works, you can figure what the increase or decrease in load is going to be as a result of those moments. So there are software packages available. The hand computations aren't very difficult, but the software packages definitely help because, again, it could be an iterative process, redesigning your pile cap to get sort of an optimal design. But there is something to talk about when you look at this formula and how it behaves. What happens if we increase the size of our footing and increase the spacing of our piles essentially to infinity? So, this graph is hypothetically a 4-pile group, and along the x-axis here, we're just increasing the eccentricity of our piles. So this is, basically we're assuming equal spacing. It's a nice square inside the square. So disregarding the moment loads, again, if you had a 50 kip load, it would be 12.5 kips per pile. So as we increase the spacing to infinity, the increase in load on your piles from that moment goes to 0. And this is an interesting phenomenon because moment equals force times distance. So if we have an applied moment that's going to be constant and we increase the distance away from the application of that moment, the only way to keep this equation true is for this force value to essentially go to 0. So obviously, you can't have an infinitely large rigid footing, and as you increase the size of your footing, maintaining that rigid size or rigid condition becomes very difficult. So, it's probably not going to be practical to have a 100-foot square building or 100-foot square foundation to mitigate the impact of your additional load. But, having said that, increasing it marginally is also going to have a noticeable impact. Through this first, few feet, you will actually reduce that additional load by quite a big margin. So, at the smallest spacing I've considered, the load in the pile goes from our 12.5 kips from our vertical load to, when you add in the moment, it goes all the way up, almost to 30 kips. So almost double what the load is. So if we increase, that spacing, we could get that down to 25 or 20. And these are pretty small numbers, but if this was a much higher load, obviously it would make a bigger impact. So really it's about the percent change of, this is a 50% drop from, 30 kips to 20 kips without, a significant increase in footing size. So you can definitely play with the size of your footing and your pile spacing to sort of mitigate some of the effects from high bending moments from the superstructure. So group effects on settlement. Whenever you've got a bunch of piles that are together, it's probably more realistic to examine the settlement of all those piles as a group. And I won't spend a tremendous amount of time on this, but basically it's designing this as sort of the projected area of where all your pile group is, and using that area to calculate settlement. And there's another approach where you're using an equivalent foundation sort of 2/3 the way down your pile depth, and you make this an equivalent footing and then go through sort of the traditional settlement calculations. And I won't spend too much time on that because that can be time consuming to talk about that. But I will talk about sort of the different conditions you may have where you may want to consider each one of these. It's perfectly fine to, for a basic assumption, just to go with this sort of overarching theory of an equivalent footing. But they have broken down all these different conditions where you've got, toe bearing and a hard clay, or you've got totally shaft resistance and a softer clay, shaft resistance. So you've got skin friction and end bearing on a hard clay. You can have all these different conditions, and basically what changes is the depth of where that equivalent footing is at and the width of that equivalent footing. So when you've got additional skin friction, the width of your equivalent footing will increase as a result of that. So it's important to, if you can get more precise with your settlement estimation, it's always going to be better. So if you know sort of what these conditions are, and can appropriately pick one of these, then you're going to have a more accurate estimation of settlement. So group effects on settlement, I'm not going to dig into this, but these are the basic, most common settlement calculations. And it's basically involving the coefficients of compressibility of the soil and how much load you're putting on that soil. So there's three main sort of different situations depending on the pre-consolidation of the soil. So if you guys have any more questions about this, I'm happy to chat in the questions section, or we can chat even offline about it. But that's all I'm going to talk about there. Now, this is where sort of things get interesting when you're looking at the lateral response of your piles. So the general assumption for a pile when you laterally load it is you're going to have a stress fold that comes off in a similar way to a stress fold that comes off from a vertical load. And if your piles are spaced too closely, you can interact with the next pile after it. Now, obviously, this is going to be very bad, not necessarily bad, but it's just something you need to consider when you have this this sort of shadowing condition from your pile spacing. Now, the nice thing about helical piles and micropiles is the shadowing assumption is basically negligible after 6 to 7 shaft diameters. And for traditional micropile helical pile design, we're already going to be out those 6 to 7 shaft diameters. So the effect of that shadowing is basically nullified. But when you do have to consider that, if you've got like a driven pile or arbor cast piles or larger diameter piles, you basically use modifiers for the PY curves to reduce the soil response, depending on what row you're in with your lateral load. So when you look back at this, if this is your first pile, nothing is hitting this one, but your second row is going to be hit. So for subsequent rows, it starts to have more and more impact on that pile's lateral load carrying capability. And again, I want to stress when you're using smaller diameter piles, that effect gets completely mitigated. So another type of pile group you may see is battered piles. And these are tremendously useful if you've got a high lateral load, so flood walls or even retaining walls, gravity retaining walls. When you've got these high lateral loads, a battered pile is very useful because a load sort of flows like water, where it's going to find the most efficient path. So a lateral load is going to much more efficiently be handled by a pile that's sort of in that same lateral plane than a vertical pile. A typical design assumption would be you design your vertical piles to carry all your vertical load and your battered piles to carry all of your lateral load. So now looking at designing, you've gone through all your group effects, you understand if you've got shadowing effects, you understand your settlements. Now it's time to basically design your individual piles. Once you've got all those sort of group effects figured out and you've identified your worst case pile, you'll basically design all piles in that group sort of using that worst case condition. So pile head fixity is just as important as that rigid pile cap assumption we talked about earlier. And what a fixed pile head is really it's saying this pile cap, instead of rotating like this top image is showing where the top of the pile is just rotating down like this, you're actually going to bend and then bend back, and there's only lateral translation at the top and no rotation of your pile. So when a pile head is allowed to rotate, you have to consider this as a pin condition versus this fixed head condition, and we're going to talk about how you look at that. And again, we need to have a rigid foundation. A flexible foundation, even with a fixed head condition, is still going to have rotation because now your actual foundation is rotating, not your pile, but your foundation, which will actually end up rotating the pile too. But when you've got a rigid foundation and a fixed condition at the top, that's whenever we see this sort of optimal scenario where the pile head is not rotating. So a fixed pile heavily restricts the displacement that you're going to see. So in these charts here, we have this bottom one is deflection, and you have 3 different head conditions: fixed head, 50% fixed head, and a free head. With the fixed head condition, having way less than the free head, and basically half of the 50% fixity sort of pin condition. So a pinned head allows for more movement of your pile, but it does help with sort of mitigating the maximum bending moment your pile is going to have. Because whenever you restrict the movement like that, your pile is demanded a lot structurally for that condition to happen, basically. So when we look at this bending moment chart at the top, if you've got a fixed head pile, we're almost at a negative 40 kipfoot moment as like our worst case moment. But for the 50% fixed, that worst case moment is around 25 to 30, which is a significant reduction over 40, and you can use a much more slender pile. So having said that, if you've got, this is going to come down to the type of structure you're doing, or whether you want to have a more fixed head or a little bit more of a pinned head that's allowed to rotate a little bit, because there is some benefit to reducing your pile section and just allowing it to deflect a bit more. But it's very important to be able to understand sort of what condition you've got. And here we're going to talk about what is considered a fixed head, and this is a topic that needs to be researched a lot more. And I'll tell you why here, because the FHWA suggests that a 50% fixity condition requires 18 inches of embedment of your pile into your pile cap, and a 100% fixed head requires a 24-inch embedment in your pile cap. So there's been a ton of research, well, not a ton, but there's been some research and studies done by helical manufacturers and researchers and academics to analyze this fixed head condition. And basically, everyone is coming to the same conclusion that your fixed head condition is a combination of your shaft size and where you're at, above or beneath your reinforcement and your foundation. And the overall finding is that this is a huge over-conservative assumption on your pile head fixity condition. So if you mischaracterize your fixity condition, looking back on these charts, you may mischaracterize your displacement and bending moments as well. So I wouldn't necessarily take the FHWA guidelines on fixed head at face value, and I'd reach out to either us or the pile manufacturers to sort of provide guidance for their specific pile types and how they make their connections. But really a general rule for like smaller diameter helical piles and micro piles is around 7 inches of embedment if you've got a bearing plate that's embedded above your reinforcement. That's going to be really close to a lot closer to a 100% fixed condition than it will be to a 50% or a pinned head condition. So PY curves are how you do the lateral load design. And this is a heavy topic, but essentially you're looking at the pile as being braced laterally by a series of nonlinear springs that may change and vary with depth and varying soil types. And there's a couple important parameters that you need to know when you're doing this sort of design, and that is this strain 50, which is the axial strain corresponding to a shear stress equal to 1/2 of a shear strength. And then the value of K is the soil modulus parameter. And this is basically a measure of the soil's resistance to lateral deflection. The good news is this is greatly simplified in programs like LPile and AllPile, because all of these PY curves and even the strain 50 and soil modulus parameters, much of this is difficult to actually measure, and you need basically empirical data to determine it. And these software packages have a bank of empirical data to help simplify that process. But when you look at it, it's so important to understand as an engineer what these actually are to help deepen your understanding of the design. So PY curves, you have your deflection Y and your soil reaction P on the Y-axis. So the soil resultant reaction is, you integrate the stresses that are forming around your pile shaft. So it's in part due to the geometry of your pile, just as much as it is the actual soil strength around it. And the deflection is obviously much more easy to visualize. It's just a measure of, okay, how much did it move with a certain load? And that's basically, in a nutshell, what the PY curves are. Without belaboring it too much, I'm happy to talk about it offline if someone wants more deeper understanding of how this works. So going through the lateral load design steps, essentially first you want to run your LPile analysis using any of the modifiers that we talked about if you've got the shadowing effects. And basically what you're trying to do is figure out sort of what the maximum deflection and what the maximum moment is on your pile. So for a group of piles, whenever you've got the interaction between the piles, you need to look at an average sort of across the entire group, and that's what this slide is demonstrating. I'm kind of speeding up here because I realize I'm running short on time. But you're basically averaging, because your deflection may be different since, again, those are going to interact together if the piles are spaced too closely. So once you've got your maximum bending moment and your maximum deflection, that's whenever you move to doing a structural analysis with that bending moment load and your vertical load. And then also looking at the sort of criteria that that project is going to have for your lateral deflection. And we'll talk about that more in a second here on this slide. These last two are basically the most critical here, where you need to determine if the pile has the structural capacity necessary to handle the moment and axial loads. And you also need to determine what is the worst case for deflection, against that worst case critical load condition. So this is sort of how you would look at the structural design for a lateral load. You've got to consider the axial load and the moment loads from the lateral loads simultaneously, because they're going to be acting on it simultaneously. If you consider them separately, your design may check out to be okay, but then when you consider it together, it doesn't check out as okay. So it's important to structurally check the combination of axial and flexural forces together before you can determine whether or not that pile is going to be acceptable. So, more often than not, lateral deflection ends up being what controls your design geotechnically. So it's not, how much the pile can hold. It's, okay, this structure can only move an inch before we have problems, so we're going to limit it to 1 inch. And AC 358 is the helical acceptance criteria document that the ICC has put out. And they basically suggest, if the superstructure isn't, tremendously sensitive to it, that a general sort of rule of thumb would be that your allowable lateral load on your pile is the load that equals to 1/2 the load that causes 1 inch of lateral movement. Now, this is for helicals. This may be different for different pile types, and it may also be different depending on whatever structure type you've got. And it may also be a different design philosophy altogether. So there's a great deal of confusion with lateral loads, but really you want some sort of limit state to be identified by the engineer of record that's going to be project specific. So it could be a limit of the ultimate deflection, and then you provide a factor of safety against that to determine your allowable load. Or they could just say, we have a limit at the allowable load of 1/2 inch, so don't go beyond that. And really you need to understand, you need to unpack that. What is the limit for this structure? Because that's going to be really critical for determining what pile type you need, what spacing you may need, et cetera, to make sure you're designing to meet that condition. So like we talked about at the beginning, all piles are going to have either one component or a combination of both, either side friction or end bearing. And I like to talk about micropiles and helicals because that's what I'm most familiar with. A micropile, is a grounded reinforced pile where along the entire length of your pile, you've got this side friction, this Fs value, and this As value would be the area, the surface area of that bond throughout the length of your pile. And then you've got end-bearing piles like helical piles where you've got some sort of end-bearing resistance that's going to be given as a pressure, so pounds per square foot, kips per square foot, whatever it may be, and then the area of that tip. And when you multiply pressure by an area, you're left with just a force that pile can hold sort of at the tip. And these values of Fs and Qp are highly specific to the soil type you've got and the pile type you're considering. So I don't want to dig into all the specifics for every type of pile together because we'll be here for 8 hours if we do that. But in general, you've got to consider this. Some sort of friction you've got and some surface area that friction is bearing against. And then at the bottom of your pile, you've got some bearing resistance and some area bearing that load into it. And this sort of design philosophy governs for, basically every deep foundation. And those are a quick snapshot of references. Again, like I talked about before, feel free to reach out if you ever need training or want to talk about any of these concepts more in depth, or you just need to bounce an idea for a specific project off of us, whatever that may be. We're always here to answer those types of questions. And like always, we'll send out a link for a quiz in the next couple days here. And once you complete that quiz, and 3 to 5 business days after that, we'll get you your PDH certificate in your inbox. And now I'm going to unmute everybody and open the floor for any questions you guys might have.
Yeah, can you explain flexible versus a fixed foundation? Pile cap. Normally, I don't quite understand flexible.
Right. I mean, so obviously concrete's not very flexible when you think about it, but it can be if the soil isn't stiff enough or the concrete isn't thick enough. You may end up in a situation where even though it's made of concrete, it is allowed to end up flexing and not acting as a rigid cap, where if you put a bending moment on it, instead of it just rotating like this and pulling up on one pile and pushing it on the other, the pile cap will actually sort of bend upward instead of transmitting that load into the piles. Does that make sense? I wish I had a better graphic.
Yeah, is that only a function of the soil, or
it's a function
most of the time you assume rigid, correct?
Yeah, you want to assume rigid, and for small pile caps, it typically is. It's a function of soil and whatever the material your foundation is made of, which is typically concrete. So it's a function of that particular site's soil conditions, as well as it is a function of the material the foundation is made of. And you can improve that rigid condition, through more reinforcement, through a thicker foundation, and there's other approaches to examining that fixed or rigid condition.
Okay, now I have another question regarding pile groups. Typically in warehouses, they might be 30, 40, 50 kip piles. The question, the total pile load. Mm-hmm. My question is, putting in 3 piles is not cost effective, and the size of the pad will be big, the cap. So, we do see sometimes 1 or 2. Now, I know 3 is preferable, but how can you compensate for that besides, grade beams? I don't know if there is a way.
Right. So, obviously grade beams will be a great way to compensate for 2 piles and a pile cap if you're, because you're going to brace it in one direction and the grade beam will brace it in the other. And remember, this is just what the IBC is suggesting you do is have 3 piles or 2 with grade beams. I have seen, very lightly loaded warehouse structures end up with only 1 pile per cap, and it's not the most stable condition and doesn't necessarily align with the IBC, but it is doable in some situations to only use 1 pile per cap. It's just definitely not the most optimal for basically really controlling those foundations, and you're allowing it to sort of rotate around your pile more than you'd like when you don't have that bracing. Not to say it can't be done, but you're basically assuming some risk to the superstructure whenever you allow that pile head or that pile cap to move around, translate, and rotate when you don't have multiple piles sort of fixing it in place. So it's not
right now, but
go ahead.
I've seen it where you've got, let's say, it could be, let's say, a 4x4 cap, mm-hmm. and and then the piles are put kind of diagonal. Now, I don't know if that eliminates, any of this teeter-totter. I think when you put 2 opposite each other, you're going to have this teeter-totter effect. I don't know how else to refer to it as. But if you put them, let's say it's a 4-foot square, and you put one at 1 foot from the end and one on the other elevation, 1 foot from the opposite end, you know, they're kind of like diagonal. I mean, does that help with the teeter-totter or not really?
If you've only got 2 pile caps and they're not tied together by a grade beam, you're always going to have that sort of teeter-totter effect, even if you put them diagonally, because you're just, instead of teeter-tottering about the X or Y axis, you're just going to teeter-totter along the diagonal axis. So that's why the IBC says, you know, 3 piles or 2 with grade beams. Certainly for lighter loaded structures, you might be able to get away with only 1 or 2, but you really need to sort of understand the owner's expectations and, you know, clearly express to them that, hey, using 1 pile is cheaper, using 2 piles is cheaper. It's probably going to support your vertical loads just fine, but there may be, you know, some, you know, less than desirable outcomes over time that could result of this, you know, sort of stability issues that you may experience by doing it this way. And it's not to say every time you will experience those problems, but you're basically opening the door for those problems to happen when your pile caps aren't braced in both directions.
Well, I'm always in favor of selling more piles. The question is, you know, can you compete if someone else is, you know,
right?
But I guess it's really down to what the engineer calls for, and then we're at risk if they do it incorrectly. So it's a challenge.
You would hope that the engineer of record has already got a pile layout and is considering the amount of stability that them as the structural engineer of record are comfortable with. Because then that takes you designing it out of it. But if you are in a situation where they haven't laid the piles out, just go in with 1 pile per column. You can do it that way, but it's probably, if you have a design submittal that you need to work through or whatever, it may get brought up that, you know, that's probably not the most stable condition for your piles.
All right, thank you.
Thanks, Kyle and Corey, for the nice comments. Well, I don't see any other questions in the chat box, or no one else is speaking up, but feel free to reach out to me anytime. I don't think I put my email address in this presentation. But you can always reach out at the email here if you did have any questions about this webinar or needed to get a hold of us. You can reach us through this link here. So again, thanks everybody for joining us today, and you know, look forward to doing this again in a couple months. So see you guys then.
Thank you.